So today I want to discuss about a polynomial problem that appeared in INMO 2020. This is a nice example to how to solve polynomial functional equations using induction. And the specialty of the problem is that it involves continuity. Now, there are very few problems in Olympiad that involves continuity in their solution. So this problem is really special. So the problem says p of x is a polynomial with real coefficients such that p of cos theta plus sin theta is same as p of cos theta minus sin theta for all real numbers theta. Then I have to prove that p can be written in the form p of x equal to a0 plus a1 times 1 minus x square whole square plus a2 times 1 minus x square whole to the power 4 plus up to n times 1 minus x square whole to the power 2, which is same as I can write p of x as a polynomial in the variable 1 minus x square whole square instead of a polynomial in x. So let's do this.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
To solve this problem, we have some key observations. First observation, you can easily see that to do this, there exists a constant c such that 1 minus x square whole square divides p of x minus c and takes c to be the constant a0. If we just see that p of x minus a0, it is divisible by 1 minus x square. So our first step should be to prove that there exists a constant c such that 1 minus x square whole square divides p of x minus c. Once we have proved that, then p of x can be written as a constant plus 1 minus x square whole square times another polynomial r of x, and degree of r of x is strictly less than the degree of p. Now we can show that r satisfies the same functional equation as that of p. Like r of cos theta plus sin theta should be r of cos theta minus sin theta. Now what is the advantage of that? Like if I can represent r in that form, I can also represent p also in that form. This is very easy to observe. Now as degree of r is smaller than degree of p, now I can do induction of the degree of polynomial so that I can apply induction hypothesis on r of x. So let's do it. Initially, what do we have? We have p of cos theta plus sin theta equal to p of cos theta minus sin theta for all real numbers theta. Say theta equal to pi by 2. Like we can put some values of theta to get some relation between p's values. What do we get? We get p of 1 equal to p of minus 1. Now to show that there exists a c such that 1 minus x square whole square divides p of x minus c, first let's show 1 minus x squared divides p of x minus c. Like x minus 1 and x plus 1 both are roots of like p of x minus c. What we can take c to be? We can simply take c to be p of 1, and that is same as p of minus 1. As we have p of 1 equal to p of minus 1, in that case x plus 1 and x minus 1 both divides p of x minus c, and x minus 1 this also divides p of x minus c, and together it implies 1 minus x square divides p of x minus c. So we have proved that 1 minus x divides p of x minus c, but I need to show that 1 minus x whole square divides p of x minus c. So let's say p of x minus c equal to 1 minus x squared times some polynomial q of x. Now to show that 1 minus x square whole square divides p of x minus c, it's enough to show that, 1 minus x square individually divides q of x. So we have in p of x minus c, like we have 1 minus x square already one factor, and another factor comes from q of x. So the whole square of 1 minus x square would divide p of x minus c. To show that, we just substitute the value, like substitute the functional equation in theta and write it in terms of q. So we have p of cos theta plus sin theta equal to p of cos theta minus sin theta. That is same as c plus 1 minus cos theta plus sin theta whole square into q of cos theta plus sin theta. This is same as c plus 1 minus cos theta minus sin theta whole square into q of cos theta minus sin theta. Now c's are cancelled out, and what will be left as minus sin to theta q of cos theta plus sin theta, these are standard trigonometric identities, equal to sin to theta q of cos theta minus sin theta. Now from here what can we say? For all theta such that sin to theta not equal to 0, we can cancel them out, and that would imply q of cos theta plus sin theta is same as minus q of cos theta minus sin theta. Now for which theta it holds? It holds for all theta such that sin 2 theta not equal to 0. And saying this is equivalent to saying that 2 theta is not a multiple of pi. So this is same as theta not equal to n pi by 2 for integer sign. Now we just use some lemma from continuity. If f maps from R to R is continuous, then if fx equal to 0 for all x in rationals, then fx is 0 for all real numbers x. Like instead of rationals, we can use any dense subset of the real numbers. So like any real number is a limit point of the set. So we can just take a sequence that converges to it. So f of that sequence should be converges to that f of that point, and the f of that sequence is identically 0. So the limit point is also, so the f of that limit point is also identically 0. So in other words, if a function gives 0 value at all rational points, it must be identically 0 on the whole real line. Like equivalently, if two functions f and g, if like fx equal to g of x for all x in q, then that would imply fx is identically equal to g of x for all x in R, given that f and g are both continuous. In this question, see, we know that for theta not equal to n pi by 2, q of cos theta plus sin theta equal to minus q of cos theta minus sin theta holds. Now points n pi by 2 is a very small subset, and it's a discrete subset of the real numbers. It doesn't matter. Like the points where they agree, it is a dense subset because it almost contains q. So like in q of cos theta plus sin theta and q of cos theta minus sin theta, both are functions in theta, and they agree almost everywhere on the real line, like almost at every point except the very small subset n pi by 2. So by continuity, q of cos theta plus sin theta and q of cos theta minus sin theta, this polynomial should be identically equal. this follows from this lemma and continuity. Q of cos theta plus sin theta equal to minus Q of cos theta minus sin theta. This holds for all real numbers theta. Now to show that 1 minus x square divides q of x, we need to show that q of plus minus 1 equal to 0. So what can we do? Like put theta equal to 0. What it will give me? Q of cos 0, that is 1, equal to minus q of 1. So q of 1 is 0. Similarly, what can we put instead? Like how can we get minus 1? Put theta equal to pi. Theta equal to pi means cos pi is minus 1. So q of minus 1 is again minus of q of minus 1. And together these two implies q of plus minus 1 equal to 0. And that implies x plus 1 and x minus 1 both divide q of x. 1 minus x square divides q of x. And this proves our claim. So our claim is proved. So from here we can say that 1 minus x square whole square divides p of x minus c. Now, so I can now write p of x equal to c plus 1 minus x square whole square into some polynomial rx, and degree of r is strictly less than degree of p. Now we can do induction on the degree of the polynomial, like strong induction. Like for base case it's easy to prove. I'll leave it as an exercise. And now for the general case, like by strong induction hypothesis, r of x already admits at the same form. Like for that we have to show that r satisfies the same functional equation as p, and that will also follow easily. Like put x equal to cos theta plus minus sin theta, we have c plus 1 minus cos theta plus sin theta whole square r of cos theta plus sin theta equal to c plus 1 minus cos theta minus sin theta whole square r of cos theta minus sin theta, and that will give me sin square 2 theta r of cos theta plus sin theta. This is same as sin square 2 theta r of cos theta minus sin theta. Now again they agree on everywhere except those points where sin square 2 theta is 0, and that is same as theta equal to n pi by 2, and as r is a polynomial, it is continuous, we can apply, like we can use the same argument as before. So r of cos theta and plus sin theta, they are continuous functions, and r of cos theta minus sin theta, and they are continuous functions, and they agree everywhere except on like multiples of integer multiples of pi by 2, and that is a very small subset, and they agree at all those points. That is a dense subset of R. So they agree everywhere for all theta in R. Now we can just apply induction hypothesis. So R can be written as the form equal to some a0 plus a1 into 1 minus x square whole square plus dot 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 something plus ar 1 minus x square whole to the power 2r. Then p of x equal to just c plus 1 minus x square times this thing. So p of x equal to c plus 1 minus x square whole square a0 times a0 plus 1 minus x square whole to the power 4 times a1 plus dot 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 dot, and this is the same of this form, and this completes the solution.
Chinta programs are designed for students who are passionate about mathematics. and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.